Okay, so hi everyone. Welcome to today or the first of this semester, so Women Network Science and Society seminar talk. So today we have a really wonderful speaker today, Deborah Sulem. I will basically introduce her a little bit, and yeah, I would just give the floor to her and start. And so she's currently a assistant professor of data science at the Università della Svizzera Italiana in Lugano. She received her Ph.D. in 2023 from the Department of Statistics at the University of Oxford and was previously a postdoc at the Barcelona School of Economics and Universitat Pompeu, Fabra. Her research interests include mainly Bayesian inference, network analysis, graphic modeling, and algorithmic and statistical fairness. So very interesting topics. So with that, I would just give it back to Deborah, and then please take it away.
Thank you very much, Yohong, for the very nice introduction. So I will try to share my slide, and please confirm that you can see them. I will also go full screen. Okay, can you see my slide well?
Yep, we can see it.
Perfect. So today in this talk, I will talk about work that I did during my postdoc on Bayesian methods and algorithms that are suitable for high-dimensional Gaussian graphical models. So before I actually talk about this work, I just wanted to present my institution, which may not be very known internationally. So it's a small university called Università della Svizzera Italiana, or called USI. And I'm based in the Faculty of Informatics, which is a department mixed between computer science, mathematics, and statistics. And which has the campus is very new and is very nice, and it's located in Lugano, which is in Ticino, the Italian part of Switzerland, and which is famous for its lake and these gorgeous landscapes. So if you get a chance, I really recommend you to visit this area. Actually, in 2026, we will be hosting the European meeting of statisticians. So of course, everyone is welcome to come to Lugano and see this area. So in this talk, I will present a work that I did jointly with my postdoc advisor, David Rossell from Pompeu Fabra University, and the former postdoc, Jack Jussen, who is now an assistant professor at Monash University. So in this, today I will try to present, part of the whole work we did, mostly on focusing on the algorithmic part. So I will first present the statistical problem that we are addressing, inferring graphical models for high-dimensional data. Then I will present the state-of-the-art Bayesian methods for doing that. And finally, I will present our proposed algorithms to accelerate Bayesian methods. And finally, if I have time, I will present some numerical results where we compare to state-of-the-art algorithms. So first, the problem that we are addressing is graphical modeling, which is equivalent to estimating partial dependencies within a set of variables. So I will call Y a random vector, so a vector of P random variables. And the goal that we are addressing is to estimate the partial dependencies within this random vector. So the partial dependency means the joint law of two variables, say yi, yj, conditionally on the rest of the variables. So it's called partial or conditional dependency. And this is also called graphical modeling because a nice way to visualize the partial dependency structure within a random vector is through a graph where each variable is represented by a node, and each edge in this graph represents the fact that two variables are conditionally dependent. And the non-edge means that two variables are conditionally independent, which is the case of y1 and y3 in this example, conditionally on y2. So one way to also represent this graph mathematically is through its adjacency matrix, which I will denote Z. So it's a binary matrix where each entry, Zij, is equal to 1 if and only if the partial dependency between yi and yj is non-null. The applications of these techniques that we target are cases where the number of variables observed are large. So P here is a large integer. One application is gene-wise association studies, where the random variables observed are the level of expression of some genes that are selected for their maybe particular role in some disease or syndrome. And in this case, the number of genes that are observed can be of order hundreds or even of thousands. And then the graphical modeling technique can be applied to infer which genes are, partially dependent in this and sort of are associated to a certain conditions or a certain disease. Another application of graphical modeling is neuroimaging data, where the variables observed can be the level of activations for each region of interest in the brain. And in this case, again, graphical modeling can be applied to infer the partial dependency structure, which informs on the dependence that exists between the activations in different locations of the brain. And in this case as well, so the level of regions analyzed can be of order hundreds or more. So inferring partial dependencies is a hard task in general, in particular if the number of variables is large. But there is one sort of simplification that we can make is if we assume that the distribution of the random vector that we observe is a normal, follows a normal distribution. So for some simplicity here, we will suppose that it's centered. So Y is a normal vector with centered around the zero vector and with an unknown covariance matrix, which I denote sigma. And this simplifies the problem of graphical modeling because there is a well-known association between the inverse covariance matrix and this graphical model. So if I denote omega, the inverse of sigma, the covariance, so it's called also the precision matrix, then the zero entries of the precision matrix encode the partial independence between two variables. So if I take two variables ij, the corresponding entry in omega is equal to 0 if and only if yi and yj are partially independent, so independent conditionally on the rest of the variables. And this means that the graphical model corresponding to the partial dependency structure of the vector y is fully encoded by the precision matrix. And I will use again my notation Z for this, the adjacency of this graphical model, where in this case, it simplifies into each entry is equal to 1 if and only if the corresponding entry omega ij is non-null. So our goal will be to estimate the graphical model from some independent observations of the Gaussian vector y. And well, actually, we will first estimate the precision matrix, which is a symmetric positive definite matrix. And from this matrix, we will deduce the graphical model by using the relations that I have just explained. So how we can do that? So actually, if we suppose that P is large and potentially even larger than the sample size n, then it is reasonable to look for a sparse graphical model, which will in particular be more interpretable. And maybe the most used method to do inference in high-dimensional graphical model is the G lasso, the graphical lasso, which is a penalized maximum likelihood estimate method. So the G lasso estimate is simply the maximizer of the log likelihood, the Gaussian likelihood, minus a penalization, which is in terms of the L1 norm of the precision matrix. The G lasso is, has some extensions where the penalization is also adapted to the different entries of omega. But in general, it has the same drawbacks as in the classical lasso in linear regression, is that it tends to shrink large coefficients. Another disadvantage of penalized MLE methods in general is that they do not provide uncertainty quantification on the estimate, and in particular here on the graphical model implied by the G-lasso estimate. And in particular, it cannot provide insights on answering questions like how likely is an edge to be included in the estimated graphical model. Another method that I want to mention is a method called node-wise regression applied to graphical modeling. So this type of method uses the correspondence between linear regression and Gaussian graphical models. In fact, so if we recall that Y is a random vector with precision matrix omega, then actually one column of omega, say the jth column, omega j, correspond to the vector of partial covariance of yj with the rest of the variables. And this means that actually this column of omega is also related to the coefficients if you regress the variable yj onto the other ones. And this can be seen by simply writing the conditional distribution of yj given y minus j, so the other variables. So if I call theta j the off-diagonal coefficients of the jth column, and if I call sigma j the inverse of the diagonal coefficients, then I can write this. So I know that yj is conditionally on y minus j is normally distributed, and actually the mean is given by the inner product between theta j and y minus j, which means that it's a sort of linear relations between yj and the variable y minus j if I condition on them. So one method that was using this correspondence is a method called penalized node-wise regression, where the idea is basically to estimate omega by estimating each column solving a linear regression problem. So each estimate of a column, so say the jth column, is estimated by regressing the jth column of the data matrix onto the other ones, also using a lasso penalization on the estimated coefficients. So this method is very beautiful because it allows to decompose a high-dimensional graphical problem into piece linear regression problems. And this P linear regression problem can be solved in parallel. So this means that the algorithm is completely parallelizable across the columns of omega. However, the estimates that are obtained do not guarantee that the estimate of the omega matrix will be positive definite because it assembles theta j's without looking at the constraint that omega needs to be positive definite, which can harm the interpretation of the estimated coefficients. So our contribution is to provide a novel Bayesian methods that leverage ID from penalized methods and this node-wise regression methods, but provides full interpretability and also uncertainty quantification on the estimated graphical model. And in particular, the algorithm is scalable to high-dimensional settings. Before I actually explain our method, I will present the state-of-the-art Bayesian methods for sparse graphical modeling. I also have a short slide on introducing Bayesian modeling in case some of you are not already familiar with. So a Bayesian method starts by a choice of prior distribution, which is a probability distribution on the space of parameters. So here the space is the space of symmetric and positive matrices, so the space of precision matrices. And given a choice of prior, the Bayesian statistician makes inference using the posterior distribution, which is also a probability distribution on the space of parameter that reflects the knowledge a posteriori on this parameter. And it is defined as a renormalization of the likelihood times the prior measure. So in a as an illustration, so the prior is the sort of analog of the penalization in a frequentist methods, and given this choice of prior, or penalty, and given the model chosen, so here the Gaussian likelihood, the posterior distribution gives gives a probability distribution on the space of parameters from which you can derive point estimates, such as the mode or the mean, and also derive some credible set that represents the certainty or uncertainty on the parameter. So maybe the most known Bayesian methods for sparse graphical modeling is using the G-Wishart prior, which is the conjugate prior for the multivariate normal distribution. And so this prior is constructed in a hierarchical manner by first putting prior on the graphical model Z, which can, for example, be a product of Bernoulli distribution on each of the edge of the graphical model. And the second part is the prior on the precision matrix given its support, so given the graphical model. And in this case, it is specified as the Wishart distribution, which is this distribution which has two main hyperparameters, a B, which is the degrees of freedom, and a shape parameter, D, which is a positive definite matrix. So this prior has the advantage that it is conjugate in the sense that the posterior distribution will also be Wishart. We'll have the form of a Wishart distribution, G-Wishart. But the problem, it has an interpretable normalizing constant, which means that to compute the posterior distribution implied by this prior, it requires some computer engineering or also some approximations of this normalizing constant. And also, this type of posterior distribution can only be computed via MCMC since it is intractable. But the MCMCs that are needed are quite slow because they can only modify one entry at a time of the precision matrix. However, it has the advantage that it's with this hierarchical structure, the G-Wishart prior is a mixture prior, which is supported also on sparse matrices, which directly provide inference on the graphical model. There is another type of prior that has been proposed, which is in the class of shrinkage priors. And it's also known as the Bayesian graphical lasso because it is really the analog of the graphical lasso in the Bayesian setting. And so in this case, the prior on the precision matrix is specified as a prior on or product of densities on each of these coefficients, each coefficient of omega. So for the diagonal entries, it's specified as an exponential distribution. And for the off-diagonal coefficient, it is a Laplace distribution. And so the Laplace distribution is a sort of equivalent to the lasso penalty, which means that there is a direct correspondence between the posterior mode implied by this prior, the map. It is actually exactly equal to the G-lasso estimate. However, this prior is not exactly this product of univariate distribution. It is actually a renormalization of this product when you apply the constraint that you want a positive definite matrix, which means that actually the marginal distribution on each coefficient are not exactly exponential or Laplace, but in fact for a large range of values of the hyperparameter lambda, then this constraint is inactive. So the marginal distribution are close to this exponential or Laplace. However, this prior is an absolutely continuous prior, which means that having a zero entry in the omega in the precision matrix happens with a zero probability, which means that it implies that also the posterior distribution puts zero probability on an event on a sparse matrix, so with zero entries. It means that the posterior and the estimates are supported on dense matrices, which means if you want to estimate a graphical model, so to find which entries can be zero or not, you need to threshold the estimates obtained with this posterior distribution. Also, it was proposed also because it has a nice, an algorithm to compute this posterior distribution can be easily coded via Gibbs samplings. updating one column at a time of the precision matrix and also under reparametrization. So because of the fact that it's an absolutely continuous posterior, there is this direct translation into a Gibbs sampling algorithm. Another prior that I want to talk about is the continuous spike and slab prior, which directly encodes the learning of the graphical model. So as I explained before, with the Bayesian graphical lasso, there is no direct encoding of the prior on the graphical model. It can only be obtained a posteriori with some post-processing. But with this prior, you can directly encode the learning the graphical structure. And this is called the spike and slab because in this case, the Laplace distribution for the off-diagonal coefficient is replaced by a mixture prior between two normal distributions, one which is called the slab, which is a normal distribution with a very large variance, and a spike, which is a normal distribution with a very small variance. And this mixture is parameterized by a weight theta. So the interpretation of this prior distribution is that a priori, so under the prior, each of diagonal coefficients, omega ij, has probability theta to be generated from the slab. And in this case, it is interpreted as a significant partial covariance. And in this, partial covariance. And therefore, it translates into putting an edge into the graphical model linking the two variables I and j. But with probability 1 minus theta, a coefficient is generated by the spike a priori. And in this case, it is interpreted to be non-significant, so close to 0, which translates into putting a non-edge or putting the variable zij equal to 0. So with this prior, the learning of the structure is directly possible. However, it's still absolutely continuous distributions. So which means that, well, Gibbs sampling strategies also applies. But from a computational point of view, it means that all the matrix computations done in the algorithms, in the MCMC, are on dense matrices, which means that for p equal to few hundreds, the algorithms is quite slow and takes few hours. And this is really because of this constraint that the posterior and the prior are supported on dense matrices. So our idea was to avoid this computational limitation due to dense matrix computation. And our idea was to replace the spike density, which was a normal distribution, by a Dirac measure at 0, which means that now under the prior, each coefficient has a probability, theta still to be generated from the slab and to be non-null. But now it has a probability 1 minus theta to be coming from the spike and to be strictly equal to 0. So to be so omega j has a probability 1 minus theta to be equal to 0. Or, again, it is almost because there is a constraint that omega needs to be positive definite. So with this prior, we can have a posterior distribution that is supported on matrices that have exact zeros, thanks to this Dirac measure at 0. Okay, so now the problem is to compute the posterior distribution implied by this prior, and this is what I will talk about now. So to compute the posterior distribution, which is an intractable distribution, then we use Monte-Carlo Markov Chain algorithms, and we design one that is that can be scalable for large P. So I recall the posterior distribution is a renormalized version of the prior and the likelihood, and it is intractable because the normalizing constant is intractable. So Monte-Carlo Markov chain algorithms are algorithms based on constructing a Markov chains between some iterates corresponding to the values of the precision matrix. So the goal is to design a Markov transition kernel that gives the dynamics of this Markov chain and which has as invariant distribution the posterior distribution that we aim to calculate. And under mild conditions, so like under standard constructions of Markov transition kernels, then we can prove that the Markov chain converges as the number of iterations goes to infinity, which means as k tends to infinity, the sample is approximately, an iterate is approximately a sample from the target distribution. However, the rate of convergence to this invariant distribution also matters. And actually, we also provide a formal analysis of the algorithmic efficiency of our Markov chain via the notion of mixing time. One thing I want to mention here is that constructing a Markov chain for precision matrices needs that you need to ensure that the constraint of the space is respected at each iteration. So we need to have updates that maintain the positive definiteness of the precision matrix. So how we do that? So one idea is to use Gibbs sampling by updating one column at a time of the precision matrix. So so it corresponds to a valid MCMC step in the sense that it leads to an invariant distribution that is the full posterior. So if we can sample from the conditional posterior distribution on one column, say omega j, given the rest of the matrix, so this contains the p minus 1 remaining matrix columns of omega, then we can construct a Markov chain by iterating over each column of omega and sampling a new column from the posterior conditional, updating that column, and then iterating over the column and repeating that for a certain number of iterations to obtain several samples from the posterior. However, in this case, the conditional posterior distribution is not directly in a tractable form. So I will try to explain that on an example. So if we consider the j's column, so here j equal to p, and we want to sample so the j column, which has off-diagonal coefficient omega minus pp and diagonal coefficient omega pp. So we propose a reparametrization that allows to have a easier form of these posterior conditionals by introducing z, which will be the vector indicating which entries of this column are 0 or not. And then given this vector z, this indicator vector, we set u as the minus the non-zero entries of this column, and v, which is a sort of a reparametrization of the variance of diagonal coefficient, which correspond to the inverse variance of the piece variable. So under this parametrization, so just to be clear, this vector of binary variable z, the vector of non-zero entries u, and the diagonal coefficient v, or reparametrized version of it, fully specify a column. So if we can specify the posterior distribution on z, u, and v, we fully specify the posterior distribution on one column. So this is the first result that we derived. We rewrote the posterior conditional distribution of one column as a product between a normal distribution on the non-zero entries, a gamma distribution for the reparametrized diagonal coefficient, and then a distribution on the set of binary vectors, which has this form, which is not so nice, not directly tractable, but it's a distribution that we can approximate via a metropolis Hastings step. So how we do that? We propose to use ideas that are already existing in Bayesian variable selection, for example. So I recall, like under our reparametrization, we will sample a column by sampling these other variables z, u, and v. And z is a binary vector, and u, which has an intractable probability density function. And u and v are a vector and a scalar, a random variable, that are distributed according to just a normal and gamma distribution. So sampling U and V is easy, but sampling Z is not directly possible. So we use a metropolis hashing step, which use a proposal distribution, which means we don't directly sample from this distribution, we sample from another one, which we set as a birth death swap proposal distribution. In 2 words, what it means is that this proposal distribution proposed to either set an entry that was 0 to 1, which is called a birth move, or set an entry that was 1 to 0, so this is a death move, or to swap 2 entries that are 0 and 1 and exchange their values. So this is one way to construct a local proposal distribution of for a binary vector Z. So with this strategy, the full algorithm is a metropolis within Gibbs, which means that we have a Gibbs structure by iterating over each column of the precision matrix. And then for at each iteration, so we consider one column, we isolate it from the rest of the matrix, and we sample first this Z vector according to our local Markov kernel or local proposal. And then we accept or reject this proposed sample with a probability, which is the acceptance ratio, which is simply the ratio of the target distribution over the proposal distribution Q. So, and once we have sampled the vector Z, then we can sample from a potentially low dimensional normal distribution for U. So the dimension will be the number of non-zero in Z, and we sample V from a gamma distribution. And then, we update the column omega, and we then omega J, and then we can update the full matrix omega. So that's the idea. That's our first proposal. We also propose to to alleviate a problem of doing local moves. When you are in a high-dimensional space, if you can only modify one entry at a time, if you can only do local moves in the space of binary vectors, then that can be quite quite slow in high-dimensional settings. So we also propose a global and independent proposal that will leverage the relationship that I explained before between linear regression and Gaussian graphical modeling. And in this case, we will also be able to leverage parallelization of the computation as done in the node-wise regression method that I presented at the beginning. So how we do that? So I recall the idea was that the one column of omega can be also obtained or estimated by regressing one variable onto the other. So say the piece column can be obtained by regressing the piece variable onto the other ones. And the linear regression coefficients are, sorry, there is a typo. This coefficient beta is basically proportional to the off-diagonal coefficient of the piece column. So if we consider the data matrix removing the piece column, and we consider it as a fixed design matrix, and we sort of analyze this as a linear regression problem, then we can also consider a prior, an equivalent discrete spike-and-slab prior on the linear regression coefficients, and compute a posterior distribution on the non-zero entry of this linear regression coefficients. So this posterior distribution, which I call linear regression posterior, has this also ugly shape, but it has the advantage that in this case, it is independent on the state of the Markov chain. So it is independent of the rest of where we condition upon. So here we were conditioning on the rest of the matrices, excluding the piece column. And it has the second advantage that this is a sort of standard posterior distribution where for which many methods have already been designed to compute this posterior distribution. So our idea is to use this posterior distribution as a proposal in our metropolis within Gibbs. Actually, we add another trick is to, for avoiding overconcentration of this proposal, we temper it, which means we exponentially exponentiate it with a power beta, which is less than 1, which sort of increase the variance of this proposal and improve the mixing of the Monte-Carlo Markov chain. Our full algorithms go like this, so it's similar to the previous one. But in this case, because the proposal distribution is independent of the state of the Markov chain, we can actually sample from it before even starting the Gibbs iteration. And we can do that in parallel for each column because we need to basically solve or sample from this p-independent posterior distribution for each column of omega. And in this sense, we call our algorithm almost parallel because at least well, the expensive part, which is sampling these binary vectors, is done in parallel. And for the rest, we have the same structure that we go over the columns. We have a metropolis async step for sampling Z, and then we sample the parameter according to normal and gamma distribution. Okay, so this was for the method. So in the few remaining minutes, I will present some numerical results. So we compare our two types of algorithms. So we have the one with the local steps, which is fully serial, and the one with the global and tempered steps, which is almost parallel because of this parallelization of the proposal that I explained. And we compare to state-of-the-art MCMC methods for Gaussian graphical modeling, which are mostly R packages, so the SSGraph package and so BDGraph package. So SSGraph implements the Gibbs sampler for the continuous pack and slab, so the one where the prior is a mixture of the two normal distribution. And then the BDGraph package implements a sampler for the G-Wishart prior, which is the conjugate prior. And actually, it has two versions, where one is called bdgraph.mpl because it uses an approximation of the marginal likelihood, so it's a marginal pseudo likelihood. Finally, we also compare to approximate Bayesian methods, which is based on a paper by Eva Chade, which aims to compute a quasi-posterior distribution. So it's an approximation of the exact posterior. So yeah, just to mention, our algorithms is already implemented in the MonBF package, which is on David GitHub webpage. So for comparing our algorithms to the state of the art, we first compare the algorithmic efficiency, which basically means the mixing time, so how fast the Markov chain converges, versus the clock time, so how much time it takes. So here we have actually a proxy measure for the mixing time. What we do is to calculate the absolute difference between the estimates obtained by two chains that are started at different places. So this gives a sort of proxy measure of the mixing time. So the smaller, the better. So and also the smaller it takes, the better. So the best place is the lower left part of this plot. So we have a setting where we sample random vector which have a precision matrix which is tri-diagonal here, and we test different setting of p, so p equals 50, 100, 200, and n is equal to 2p in this case. And the trend we observe across all simulations is that, well, the fastest and the better mixing method is always the approximate Bayesian method. So the quasi-posterior method is always the fastest, thanks to the approximation it does. And our method is the serial and the serial algorithm that we propose based on the local step is the second best. The one that is not too far is also the one from bdgraph.mpl, and also in this case, the global method performs worse than the local one. In this case, probably because the posterior is quite concentrated, and in this case, doing local moves is enough, let's say, whereas global moves can actually slow down the process. Also, not surprisingly, the slowest method is the continuous pack and slab prior method, which is at the top. And so we see that this trend repeats over different values of p and also n. To finish, I have a last slide to show where the global steps can be advantageous. And actually, it's not in it's in particular cases that it can be advantageous to do global steps. In particular, when the precision matrix is ill conditioned, so when it has a very small eigenvalue. And in this case, this usually implies that the posterior distribution is multimodal. And to explore all these modes, doing local moves can be quite slow. But with these global steps, we can be much faster. And that is what we observe in this case. I don't remember exactly the value of the smallest eigenvalue. But we observe that in this case, the mixing time is is much better for the global and tempered metropolis within Gibbs than for the serial ones. So this is like the interest of the global steps for, in particular, multimodal posteriors. And with this, I can summarize and conclude my talk. So in this work, we propose novel MCMC algorithms, more precisely metropolis within Gibbs, for high-dimensional Gaussian graphical models, which are based on a fully interpretable prior, the discrete SPAC and SLAB. And these algorithms are already implemented in the R package, which will be on CRAN soon. So to design efficient steps, we propose to do local or global steps. And with the global steps in particular, we can leverage algorithms that are already existing for linear regression. And also we can parallelize a part of these computations. We also provide a theoretical analysis of this metropolis within Gibbs algorithms through their mixing time, so the time to convergence. But that is still work in progress and will be in our preprint, which should be out soon. And with this, I conclude and thank you very much for your attention.
Thank you for the very talk. So I will stop the recording. So so if any person have questions, we can